The State and Future of Quantum Computing, a 500-year horizon. Quantum computing isn't just another advance in technology. It's a fundamental shift in how humanity processes information, understands the universe, and even imagines the future. This is the story of where it began, where it stands today, and where it might be heading over the next 500 years. Chapter 1. Foundations. At the dawn of the 20th century, physics faced a crisis. Classical mechanics couldn't explain the behavior of atoms and light. Out of that chaos emerged quantum mechanics, a radical theory revealing that particles could exist in multiple states at once and influence each other instantaneously across vast distances. These principles, once thought philosophical curiosities, became the seeds of a future where information could be manipulated in fundamentally new ways. Quantum mechanics didn't just disrupt physics, it reshaped our entire conception of reality. Concepts like superposition, entanglement, and wave function collapse were more than just mathematical abstractions. They hinted at an underlying reality that defied common sense. In the decades that followed, these ideas were put to the test through thought experiments and laboratory investigations. And while they puzzled even their greatest discoverers, the accuracy of quantum theory was beyond question. This paradox, the beauty and strangeness of the quantum world, would eventually inspire a new vision, to build machines that operated by these same rules. In the 1980s, visionary physicists like Richard Feynman and David Deutsch proposed that quantum phenomena could be harnessed to process information. Their theories laid the groundwork for what we now call quantum computing. Unlike classical bits, which are either 0 or 1, quantum bits, or qubits, can be both at the same time. This allows quantum computers to explore vast solution spaces in parallel, unlocking new potential in chemistry, cryptography, optimization, and beyond. Deutsch went further than Feynman, proposing the idea of a universal quantum computer that could simulate not just physics, but any computable process in the universe. He suggested that quantum computers weren't just powerful, they were fundamental to the very nature of reality. Today, those ideas have become a global scientific mission. Governments, companies, and universities are racing to turn the theory of quantum computing into practice, each step of progress reinforcing the possibility that our future will be built not with silicon alone, but with the strange rules of the quantum world. Chapter 2. Where we are today, 2025. The present era is what researchers call the NISQ era, Noisy Intermediate Scale Quantum. Today's machines, while still error-prone, can perform computations that hint at the power to come. Quantum processors with 50 to 100 qubits can't yet outperform classical machines on most tasks, but they are closing the gap. Multiple technologies are competing to become the foundation of quantum computing. Superconducting circuits, trapped ions, photonics, neutral atoms, and even exotic topological particles. Each of these systems has its own strengths. Superconducting qubits are fast and easy to manufacture but short-lived. Trapped ions offer incredible precision but are slower and harder to scale. Photonic systems operate at room temperature and promise high-speed data transmission. Neutral atoms offer flexible scaling, and topological qubits promise built-in error resistance, if we can ever build them. This diversity in approach is one of the field's greatest strengths. Like the early days of aviation or computing, no single paradigm has emerged as the winner. Instead, the race is driving rapid innovation across multiple disciplines. Condensed matter physics, electrical engineering, computer science, and materials science all play essential roles. The software ecosystem is evolving alongside the hardware. Developers now have access to platforms like IBM's Qiskit, Google's Cirq, and Xanadu's PennyLane. Researchers are designing quantum algorithms to tackle problems in optimization, material discovery, financial modeling, and machine learning. Techniques like the variational quantum eigensolver, VQE, and quantum approximate optimization algorithm, QAOA, are already being tested for practical value. Quantum error correction, once considered a theoretical ideal, is now an engineering target. Promising techniques like surface codes and cat codes are being implemented on prototype systems. These methods are essential for building scalable, fault-tolerant machines, but they require thousands of physical qubits for every single logical qubit. This is why we are still years away from building large-scale systems. Governments and corporations are investing heavily. Over $50 billion has poured into quantum technologies globally. National quantum initiatives in the U.S., Europe, China, and Canada are funding research, education, and commercial development. Yet with investment comes concern about national security, corporate monopolies, and the risk of creating a new technological divide. If only a handful of countries or corporations control the quantum future, what will that mean for the rest of the world? The challenge of the present moment is to scale, to stabilize, and to democratize. The breakthroughs of this decade will define who has access to quantum power in the next, and for what purposes it is used. Chapter 3. The Coming Decades, 2025 to 2100. As we look toward the next 75 years, quantum computing is expected to evolve from an experimental technology into a mature platform for solving previously intractable problems. This transition won't happen overnight. It will unfold in stages, each defined by critical breakthroughs in scalability, fault tolerance, and hybrid architectures. From 2025 to 2040, we will likely see steady advancements in noisy intermediate-scale quantum devices. These machines won't yet replace classical supercomputers, but they will begin delivering utility in specialized areas. Pharmaceutical firms may use quantum processors to identify new molecules. Logistics companies might optimize routes with hybrid quantum classical algorithms. Financial institutions could explore quantum Monte Carlo methods to refine risk models. Governments will play a crucial role in this phase, not only funding research, but also regulating access and setting standards. The development of quantum-secure communication networks, known as quantum key distribution, QKD, will be prioritized. These systems use entangled particles to create encryption keys that are fundamentally immune to eavesdropping. By 2040, quantum-secure data channels may be standard in defense, banking, and critical infrastructure. As we approach mid-century, the first fault-tolerant quantum computers could emerge. These machines, protected by layers of quantum error correction, will unlock deep quantum circuits capable of modeling large molecules, simulating high-energy physics, and solving certain mathematical problems orders of magnitude faster than their classical counterparts. Their emergence will shift quantum computing from novelty to necessity. Between 2050 and 2100, we may see the rise of the quantum Internet. Built on entanglement and teleportation protocols, this network will connect quantum devices across cities, continents, and eventually, planets. It will allow distributed quantum computing, enabling resource sharing between laboratories, universities, and companies. In this world, quantum computing will no longer be confined to elite institutions. Just as today's smartphones have more power than the mainframes of the 1960s, tomorrow's portable quantum devices may empower individual scientists, students, and creators to contribute to global innovation. Ethical questions will become more urgent. If quantum computers can decrypt encrypted data from decades past, how should we manage historical secrets? Should quantum algorithms be allowed to design policies that impact millions of lives? What happens when decision-making moves beyond human comprehension? Education will adapt in response. By the end of the 21st century, basic quantum literacy may be as essential as reading, writing, or algebra. High school students might run experiments on cloud-connected quantum systems. Universities will offer interdisciplinary degrees in quantum information science, blending physics, computer science, ethics, and law. This century will be remembered not only for its technological progress, but for how humanity chose to integrate that progress into daily life. The challenge will not just be to build the machines, but to build the society capable of using them wisely. Chapter 4. The Far Horizon, 2100 to 2525. Projecting 500 years into the future may seem speculative, but the history of computation gives us reason to believe the change will be profound. In just a few generations, we've gone from vacuum tubes to cloud AI. Imagine what another 20 generations could accomplish. By the early 2100s, fully error-corrected quantum systems with millions of logical qubits may exist. These systems will be capable of simulating entire cells, organisms, or even ecosystems in real time. Medical treatments will become ultra-personalized, modeled first on quantum simulators before being deployed. Climate policy could be tested in advance, using quantum models that factor in thousands of interconnected variables. Quantum computing could also converge with artificial intelligence. Quantum-enhanced AIs might be capable of solving optimization problems with breathtaking speed. They might develop new languages, design new materials, or even propose new scientific laws. As AI and quantum computing blend, we may see the rise of quantum cognition, new architectures of thought that go beyond human reasoning. Beyond Earth, interplanetary colonies may use entangled satellites to synchronize operations across vast distances. On Mars or in orbit around Jupiter, researchers could access shared quantum states with their colleagues on Earth. This would enable secure, instantaneous coordination, an essential tool for spacefaring civilizations. By the 2300s, quantum computing could become so integrated into our infrastructure that it's invisible, like electricity today. It might manage weather systems, direct autonomous fleets, or run predictive governance models for entire populations. But invisibility comes with risk. We must remain vigilant about transparency, control, and ethics. We must ensure these systems enhance human agency rather than replace it. And in the 2400s and beyond, a final frontier may emerge: quantum consciousness. If quantum computing merges with neuroscience, we may unlock new forms of awareness. Machines may begin to model subjective experience. Memory, emotion, and even identity could take on quantum characteristics. Whether these entities are considered alive or something new entirely will be among the greatest philosophical questions ever asked. This era won't just test our technologies. It will test our values, our empathy, and our capacity for wisdom. The power to simulate reality must be met with the responsibility to preserve it. Final reflections. Quantum computing is not just about computation. It is about transformation. A transformation of science, society, and self. From the early dreams of Feynman and Deutsch to the interstellar civilizations of tomorrow, quantum computing holds the promise and the burden of reshaping reality. How we approach this journey will define our species for centuries to come. The future will not be written by machines alone. It will be written by the choices we make about equity, ethics, curiosity, and courage. This is not just a story about qubits. It's a story about us, written and narrated for the next era of discovery.